All right, so we're going to talk about some new properties. Please listen. You haven't learned these before, but you know these properties of exponents. And so let's think about if we have, you don't have to write this down, but if we have this, we're multiplying that the same base. What do you do with the exponent? Oh, is it messed up? Thank you. Right, you would add. And so with exponents, multiplication and adding are correlated, and it's the same thing with logarithms because a logarithm is just another way of writing an exponent. So anytime you have the logarithm of two things multiplied by each other, two factors multiplied by each other, you're actually going to separate them into two logarithms that are going to be added. So it's just like adding exponents when there's multiplication. All right, what about whenever you're dividing? So let's say you had x to the fifth divided by x to the second. What would you do with those exponents? You would subtract. So exponents, division and subtraction are correlated to each other. It's not a good place to put that. I've already graded those. And so with logarithms, if you have the logarithm of two items divided by each other, you're going to subtract the logarithm of each of those, just like that. All right, and then one last property. And this is the one that most people don't remember. If you have power raised to power, what do you do with those powers? You multiply. That would be x to the sixth. And so that's kind of related to this power property. So if you have the logarithm of a power, you actually end up multiplying by that power. Right, and these properties go both ways. Most of the time, we're going to use these properties in reverse. So it's more beneficial to us, what we have to do, to write multiple logarithms as one logarithm, which is what we're going to do on example 1. All right, so for example 1, we have log base 4 of x plus log base 4 of y. So we're going to bring that as one logarithm, and the base obviously is going to be the same, log base 4. All right, so if we have two logarithms added, what do you think we use to bring them together as one logarithm? Multiplication. So it's going to be log base 4 of xy. All right, and then for b, we have the natural log of 5 minus the natural log of z. So we're going to bring that together as one natural log. And since these logarithms are subtracted, we're going to bring them together using division. Now, one thing I like to talk about, because it gets a little confusing when we start seeing ones like C. So you can think of subtraction kind of like a negative exponent. So if there is subtraction in front of that logarithm, that part of the argument is going to go in the denominator. And then if it's positive in front, then that part of the argument is going to go in the numerator. All right, so let's look at C. We're going to bring this together as one logarithm, log base 10. And if there's subtraction at all in your problem, you are definitely going to have a fraction in your argument. So you can go ahead and just draw a little fraction bar. All right, so if it's positive, then that argument is going to go in the numerator. So that's why x is in the numerator. If the logarithm is negative in front, that argument is going to go in the denominator. So 5 goes in the denominator. Z is also going to go in the denominator, and it is just going to be multiplied by the 5. Now that confuses people the first time they see it, but hopefully you'll kind of get it in your head. When you bring these together, you're either multiplying in the numerator or multiplying in the denominator, or it's just one thing divided by another. All right, y'all okay? Okay, let's look at another one. All right, so we're going to start using that power property. So if there is a number in front of the logarithm, it is getting bumped up to an exponent. So we have two logarithms that are separated by subtraction. So we're going to bring them together using division. That 3 becomes a power on the x, and so it's x cubed in the numerator and y in the denominator. All right, and then E is going to use all the properties. So all these numbers that are in the front are going to bump up to exponents. We're going to have 1 log base 7. All right, and then anytime there's subtraction between your logarithms, we are going to have something in the denominator, so you can go ahead and draw a fraction mark. All right, so that a squared is going to go in the numerator, b to the 5th in the denominator because there was subtraction in front of it, and then 4 to the 1/2 is going to be multiplied in the numerator. Let me move this a little bit. We are not going to leave it like that though. So what does it mean to raise something to the 1/2? Square root, nice. So I'm going to rewrite this as the final answer. So that's just going to be 2a squared in the numerator and b to the 5th in the denominator. So if you can do one like E, you understand the properties. Like that's using all the properties different ways. Bless you. All right, what questions do you guys have so far? Because the last one is kind of weird. We'll figure it out though. Yes, sir. On D? You're welcome. Okay, so let's look at this F. We don't have 2 logarithms, so we can't bring them together as one logarithm if one of them isn't a logarithm. So what we're going to do is write 2 as a logarithm. So it's going to be log base 6 of something. That should equal 2. Any ideas what that something is? If you did log base 6 of it, you would get 2 because the power would be 2. Say it again. We want to, basically, what's in there would be what you would get if you did 6 to the 2nd power, which is, thank you. Whoops, I was writing it backwards. So log base 6 of 36 is 2. So I can rewrite it that way and then have a plus log base 6 of x. So now I can bring those together as one logarithm. Kind of tricky. Sometimes these require you to think a little more than other times. Okay, so that's basically the properties, using them to condense, which in my opinion is a little more important for what we have to do in the future with logarithms. But we do need to know how to go the other way also. So it's written on example 2 is written as one logarithm. We want to write it as multiple logarithms. All right, so because these items in the argument are being divided, when I write these as separate logarithms, I'm going to subtract. And when you're writing as multiple logarithms, like each little thing gets its own logarithm. So x gets this logarithm, y gets this logarithm. That is not one of the answer choices. So what do you guys think we need to do? The 2. So the power property tells us we can take that 2 and multiply it by the front of that logarithm, and that's going to be c. All right, you guys okay? All right, example 6 is another one where we have one logarithm and we're going to write it as multiple logarithms. These directions are kind of interesting, actually. So we have f of x is log of 6x. That's going to be a horizontal dilation of the function g of x, which is just log of x. So what is the factor of the horizontal dilation? If it's a 6 here, 1/6. That's just a little reminder. Okay, so we're going to show that f can also be written as a vertical translation. So that's something that the standards in this class talk about multiple times, how you can start with a horizontal dilation, rewrite it, and now it's some kind of translation. That's new to me. Like that's not something a class I've taught that we've ever focused on, but it comes up again and again in this class. So I'm willing to bet it's going to be on the AP test. So anyway, we want to write it so f of x is g of x plus some constant. That would be the vertical translation. So what they want us to do is just take f of x, which is this, and use the properties to write it as multiple logarithms. So since 6 is being multiplied by x, we would write it as two logarithms that are added to each other. And we're pretty much finished. We just have to answer the question. And so g of x is log of x. So this basically is that. So that's going to make k log of 6. Log of 6 is a constant. I typed it last period. It's 0.7781512,504. So it's just a value that's being added to that other logarithm. All right, any questions on that? Okay, so that takes us to the last property we're going to talk about today, which is the change of base property. Now back, I don't know how long it's been, it's, I don't know, 10, 15 years. These calculators didn't have the log base. So when you do alpha window, you see the log base where you can find the logarithm of any base. We could type in log base 2 of 9 and it would give us the answer. We didn't used to have that. But we did have the log and natural log buttons. And so we would use the change of base to figure out what log base 2 of 9 is. And then I quit teaching that because it felt like it wasn't necessary. Like we could figure it out using the other calculator. And then I saw a question that used the change of base on the ACT. So I started teaching it again. So we're going to learn it. It might be on the AP test. It might be on the ACT. If it is, it's super easy to get right if you remember the formula. And so what the change of base formula tells you is if you want to change it to any base in the world, typically it's either the common log or natural log that's in your calculator. You just do log of whatever base you want of the argument divided by log of whatever base you want of the base. All right. So on example 4, we're going to do 2 of these. So we're going to do a ratio of common logs and a ratio of natural logs. So common log is log without a base, log base 10. So in the numerator, it's log of the original argument over log of the original base. So that question on the ACT, you can, if you remember this formula, you can get right in like 5 seconds. If you hadn't seen it before, you'd have to try a bunch of stuff in your calculator until you figured it out, which would take longer than you would want at that point. And these are typically questions towards the end. The logarithm questions are towards the end of the ACT. All right, and then natural log is just natural log of x over natural log of 3. Okay, you guys try B on your own, please. All right. And then if you notice in this box, there's another vertical dilation relationship between logarithms. And so that's what we're going to talk about in example 5. So f of x is log base 4 of x. G of x is log base 9 of x. We want to show that F is a vertical dilation of G by finding whatever K value is that we would multiply by. All right. So what they're telling us to do is to rewrite this using base G. Not G, 9. I don't even know what I said. Rewrite using base 9. So instead of doing common log or natural log, we can do any log in the world. What we want for this particular problem is log base 9. So should it be log base 9 of x in the numerator or log base 9 of 4? X in the numerator, good. Log base 9 of 4 in the denominator. All right, so g of x is log base 9 of 4. So we want to do this right here. So it's going to be k times g of x. All right, so if we look at this, what are we multiplying log base 9 of x by? I'll give you a hint. It's a fraction. We're multiplying by 1 over log base 9 of 4. Is that what you said? I didn't think so. It's okay. So that's what k is. 1 over log base 9 of 4. Now, in my opinion, that is a very tricky question. We're going to talk about logarithms for a little while longer, and then we're going to talk about trigonometry for a long time. If you saw this question on the AP test, it's going to be a very difficult one to get right. Like, we'll review, but I think that's pretty advanced. It's doable, but you just have to remember a lot of things. All right, so what questions do you guys have on these new properties